So Brendan Guilfoyle from Surrey, and he's going to talk to us on a global version of the classical result of Joachimsthal and the slice problem from maths. Thanks, Brendan.
Thank you, John. So yeah, it's been a year and a bit, I think, since I've been here before, and I guess last time I was here I talked a little bit about our proof of the global Kaehler conjecture and the way in which we developed some tools to prove the local version through semi-local arguments. So the talk I'm going to give now is kind of pushes that in a certain direction, in a more topological direction still, and along the way it gives us a nice, well, I'll let you decide, but this extension of a classical result going back 150 years of Joachimsthal. So let me just start by stating a theorem, which is always good to do in maths talk. So classical differential geometry, so let S1 and S2 smooth, convex. I'll take closed, although the statement of this theorem is not optimal, there are sharper results, but I will just do it for the purpose of this talk. I'll take it to be smooth, closed, convex surfaces in R3. So intersecting at constant angle. So the result of Joachimsthal, I guess it's, so we'll get this right, 1846. In 1846, I guess the special case, and Bonnet did the general case in 1853, states that if the intersection curve is a line of curvature in one of the surfaces, it's a line of curvature in the other. So I guess if I come back up here and intersecting constant angle on curve C, then the statement is if C is a line of curvature, on S1, then it is a line of curvature on S2. Okay, so this is a classical result, obviously, and it's stated in many textbooks of geometry and the proofs given. What we're going to talk about is the following global extension of this, which is, so this is, of course, with Wilhelm Klingenberg. So I guess we'll put a preprint in the archive at some stage shortly. So the statement is that, okay, so let me just quickly get a picture of this just to assist us in the statement. So here's your two convex surfaces intersecting on this curve C. Let's call that S1 and call that S2. So what I'm interested in just in this picture here would be the disk that this intersection curve spans on S1, one of the disks, the outer one here, and the outer one here in this picture. So let's call that disk 1 and disk 2. And the statement is that the total umbilic index of D1 is equal to the total umbilic index of D2. So here, the index of the disk is the sum of the number of umbilic points in D counted with index. So if you recall...
So Brendan, when
yes?
you say disk, you're meaning, because my surface may not be topologically a sphere.
Closed, convex.
Oh, convex, okay.
Sorry.
Okay, good. Thank you.
That's why, okay. So there is a more general statement in which I can just talk about indices of a winding number around the two.
Okay.
But let's just focus specifically on two spheres intersecting. So these are topological, these are disks.
Okay, very good.
And we have a notion of outside and inside because they're all oriented, so we can take two outside ones on the intersection curve. Okay, so umbilic point here, of course, refers to the second fundamental form. The second fundamental form of your surface is a symmetric 2x2 matrix, and it has eigenvalues. When the two eigenvalues are equal, then you have an umbilic point. So these would be points where the surface looks a little bit like a sphere.
So at the intersecting curve, you also may have umbilic points?
Okay, so I should say without umbilic points, yes. Thank you. Otherwise, that's not well defined. So it can't have umbilic points on either surface. Thank you. Yes, so that certainly is true. Okay, so Okay, so why would we call this global version? Because of course, well, I guess this thing here works for any piece of the curve, right? If any small piece of a curve is a line of curvature, it's going to be a line of curvature on both. Whereas here, this refers to a disk enclosed by a curve. In fact, this is a winding number argument, and it's subtle. It's a subtle property. What it means is, as you move these two intersecting ones, if an umbilic point is going to cross on one, it's going to cross on the other as well, so that this total number of umbilic points remains the same. Excuse me, on both sides. The index is, of course, of the umbilic point is the winding number of the principal foliation, the curvature foliation at that point, and this is what we're counting with that index. Okay, so this result, I guess I'm not going to, what I hope to do in this talk is not so much talk about the proof of this result, because, well, it has a certain elegance and niceness in it. It shows a certain efficiency in some computational techniques. But what I want to focus on is how we came to this result, and also how to interpret it, and in particular how that relates to the slice problem for knots. Now, in that, you'll see we have a much bigger goal in mind, and one that I'll need a little bit of justification for. So just to outline what I'm going to talk about, so we're going to change gears. I'm going to just talk a little bit about the geometrization of four manifolds. Seems like a disjuncture, but we'll get back to why this has got anything to do with this theorem. The second thing I'm going to talk about is Casson angles, which are the key to understand the complexity and difficulties inherent in four manifolds. And then I'll come back to Joachimsthal theorem, this global version that we have presented here. Okay, so in some ways now I'm going to just ask you to forget about this for a second, and then we'll come back and we'll say, well, what on earth has any of this got to do with Joachimsthal, and hopefully at the end you get a big surprise. Okay, so I'm going to start out, well, as this is a geometry day, as it were, I'm going to just talk a little bit about what kind of motivation, or what the issue of geometrization of four manifolds. So to do that, let me just compare with a number, well, lower dimension. If you look at dimension, so in dimension 2, of course, actually I might make myself a little bit more space here so I can fit it in, but you don't want to all together onto the next board. All right. So, the geometrization. So the issue of geometrization and classification. So, of course, the well-known classification of two manifolds, the geometry that you look at is, of course, H2, S2, and R2, and the quantity that you use to measure, or the geometric property that you use, is, of course, Gauss curvature. And then you can classify all closed compact surfaces using just the Gauss curvature of the metric that you have on your surface. For three manifolds, then you have the 8 Thurston geometries, as recently completed by Perlman. And you have, what is the quantity? Well, here things get a little bit more complicated. You have to have some kind of group action, a homogeneous group action, but there's certainly a well-defined geometric ansatz, if you like, which organizes these four manifolds after you cut them up and do certain topological, you cut them into prime manifolds. Now, of course, for four manifolds, all I'm going to have to put down is question mark, question mark, question mark, because, to be honest, there's simply nothing in sight at this point to tell us as to why, what kind of geometrization would even be possible for four manifolds. Okay, so in that context, I'm going to just make a few comments. So my comments in the first part are going to be somewhat negative as to how what we would even possibly mean about geometrization of four manifolds. The first one is well-known one, and this is new, is of course that every finitely presented group is pi1 of some smooth compact four manifold. So immediately, when you start talking about classifying, or these four manifolds, of course you hit the word problem. For in its full generality, the possibility of classifying four manifolds in any, whether it's geometric or in any manner, comes under question because of that. Can you classify four manifolds? Well, that's got a lot of practical problems. Okay, so what's usually done is, of course, you look at just simply connected. You kind of elide that whole problem, and you just look at simply connected four manifolds and hope that you can say something about that. Okay, so that's nothing to do with geometry per se. On the other hand, what would you do here? You notice, of course, a Gauss curvature homogeneous. What possible curvature relations would you introduce, or restrictions would you introduce, which would be sensitive to the topology that underlies it? And here, the fundamental geometric problem is curvature weakens and higher. Weakens as dimension increases. As your dimension increases. So scalar curvature is no good, Ricci curvature starts getting weaker and weaker. So what you find if you try and introduce nice curvature conditions to restrict the four manifolds, or to detect the topology of your four manifold, what you find is you have to impose very, very strong conditions like positive curvature, which of course gets more, and it's a bigger and bigger imposition the higher dimension you go. So certainly curvature as a tool to geometrize four manifolds, even simply connected four manifolds, becomes a little bit of a problem. Or at least has a lot of questions that you would have to address before you could consider this as any kind of viable program. Okay, so what I want to take though on a more positive side is just to note, going back to the earlier cases, what would you expect? What kind of clues are given to us as to how we might go about this problem? The first thing you might say, or the first thing we would say, I would say, is that dimensions feed into the higher dimensions, or you would say lower dimensions. So lower dimensions, high, feed into higher dimensions. So in other words, as you go up in dimension, the complexity of your situation should always include all the lower dimensions. So for example, if you take the two-dimensional one, of course this is all pi 1, basically it's on pi 1. You look at curves on the surface, the generators for the fundamental group, and then, so for n equal to 2, you have just pi 1 of your surface, which is of course a fundamental tool in which you would use in describing that. For three manifolds, of course, well, for three manifolds, you could never think of the classification of three manifolds without having Heegaard splittings. The Heegaard splittings are surfaces sitting in three manifolds. So for codimension 1, you would use Heegaard splittings and the whole theory of surfaces and the way in which the fundamental groups sit inside each other, etc. On the other hand, what about codimension 2? Well, of course, knots. Knots in three manifold are a key ingredient in understanding three manifolds. So there's simply no way that you could understand three manifolds unless you know how all these four manifolds, two manifolds could sit inside, how these one manifold, and the relationship between them. So what I would say is for four manifolds, there is simply no possibility that we're going to get anything sensible here unless it incorporates the lower dimensions in some way, in some very tangible way. The second thing I'd say is as I guess in all classification, in a lot of mathematics, one has to be somewhat opportunist. And one thing that certainly I would say is extremely important is that in all of these cases, of 2 dimensions, 3 dimensions, you exploit accidents of low dimensions. So in fact, I would even go further. I'd say you have to multiply exploit accidents of low dimension. So somehow, the fact that you're in low dimension allows you to classify, simply because there's all these accidents that occur with these low dimensions, which then gives you the handle as to how to get into finding classification and geometrization. So for example, you can never think of surfaces, going back to our picture there of Gauss curvature, etc., without understanding, the relationship with Riemann surfaces. View them as a complex structure in two manifolds. Of course, that's a key element. The conformal factor is the geometrization conjecture, is the uniformization of surfaces. On the other hand, say take dimension 3. Well, these 8 geometries, why 8? Well, again, it's accidents of low dimension. So the 8 Thurston geometries are, of course, very specific to 3 dimensions. Even more than that, I would say, even at a technical level, Perelman's flow results do not work in higher dimensions. So his resolution of singularities is heavily dependent on dimension 3. It's only in dimension 3 that those theorems go through. So even at both at a philosophical level, but also at a practical level, you have to exploit this low dimensionality, the fact that it's dimension 3. Otherwise, you simply wouldn't be able to complete any program which would attempt to classify or geometrize in some comprehensive way that dimension. Okay, so this is just, I guess, just random thoughts in some way on what I would view as the important aspects of geometrization, what we can learn in lower dimension, and how we can possibly try and implement it in dimension 4. So for dimension 4, as one part of some ultimate geometrization, loosely interpreted, is that neutral metrics will play a very important role. So the proposal is use neutral metrics, and here I mean by neutral, I mean the signature is plus, plus, minus, minus. So it's indefinite signature, 2, 2, split signature metric. Is to use this in some sense on 4 manifolds to see the topology. In some sense, I guess, you know, when I talked about geometrization and the picture I just in the curvature, etc., I was talking about positive definite metrics, obviously. So here what I'm saying is now what we should look at in 4 manifolds is the neutral metrics, and that these neutral metrics see the topology of the 4 manifold. Okay, so the proposal then is, I guess, the idea, this neutral metric coming from a kind of relativistic plus, 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 minus background, I tend to call this a kind of a causal topology, where causality is related to the signature of the objects that you, of the induced objects that you have in the 4 manifold. Okay, so let me be a little bit more concrete about that. How do I mean that neutral, what do I mean by telling you that neutral metrics of this signature actually see the topology of your underlying 4 manifold? Okay, so let me give you just 2 insights into that, and then I'll talk a little bit more about 4 manifolds and the problems of 4 manifolds before coming back to Joachimsthal. So the first thing we'll say is the following. So this is in the closed case. So a necessary condition for a smooth 4 manifold, closed, without boundaries, smooth 4 manifold, to admit a neutral metric is, well, it's a topological condition. It's a topological condition that says the Euler number of your 4 manifold, let's call the 4 manifold W, goes with 4 manifold called W, plus the Hertzsprung signature must be equal to 0 mod 4, and also the same thing with the minus, equal to 0 mod 4. So on the one hand, you could interpret that and say, well, that's very negative. It means very few 4 manifolds actually have neutral metrics, so how can you possibly even, well, okay, but I'm saying this is the closed case in the first instance, but also it indicates that your metric somehow, there's an obstruction to your metric existing. It sees the topology of the 4 manifold. Okay, what about, I didn't say anything about what that 4 manifold was. So if W is simply connected, the conditions are sufficient. So in the simply connected case, this is an if and only. The conditions are sufficient.
So if you add those 2 equations, you also get that chi of W?
Sorry?
If you add those 2 equations, you get that chi of W is 0 mod 4, yeah?
Yeah.
And if you subtract them, you get,
No,
you get 2.
2.
Yeah.
So the chi and sigma should both be even.
Yes. Yeah, you can. Okay, so for example, this will rule out S4, okay? So it'll rule out certain, it doesn't rule out, for example, K3 manifolds. So in fact, there exists K3 manifolds, these are open, and I'm not going to address any of these issues as such, because I'm not interested in the closed case. But again, I'm just taking this as an off-the-shelf rule to show you, okay, so this, I guess, is known, you could go back to a paper of Heinz, Hopf and Hertzsprung, I think, from the 50s, I guess, for the first one. This condition here is Matsushita in 1988. So this gives you restrictions on when you can have a neutral metric on a four manifold, on a closed four manifold. So, and as I you can say CP2 doesn't have one, but if you connect enough of them, you can, and you can start playing closed topological constructions and until you find it, etc. Okay, but I'm not particularly interested in the closed case. In fact, what I'm interested in is the case with the boundary where there is no obstruction, but you can see the four manifold, the metric of the boundary.
So
Yeah.
what's the simplest example when you have
S2 cross S2. With plus and minus. I think that's probably the simplest closed case. Okay, so that's one thing. But again, notice this is in distinction from the definite metric. There's no obstruction to a definite metric on a four manifold of any sort. So again, the idea is that somehow neutral metrics are sensitive to the topology of the underlying four manifold. And in the closed case, one could say fatally if one is being one were being negative. However, again, I'm going to put that all aside. What I'm interested in is the case with boundary. So the boundary case. So what I'm going to say here is I'm just going to give you a simple example, the simplest example, and show you that somehow there's a remnant of the interior of the manifold at in the boundary of it when you have a neutral metric. So, so the example, so I'm not going to write down the explicit map, is that if you take R22, so let's just take the simplest case, take flat metric plus plus minus minus on R4, so let's just call it G for G flat metric. There exists a conformal compactification of this into the four ball with a neutral metric, which is conformally related to the so this map here. So such that this is omega of G. So there's your conformal factor. Your conformal factor is 0, on the boundary of the four ball. So the points at infinity in R22 are being brought to the S3 boundary of this four manifold by this map. It's a conformal scaling, so for example the null structure is going to be preserved, so it will have certain remnants of the geometry from here will be there. And the boundary of this four ball has the following properties. The first property is that it's null. It's a null with respect to the all with respect to this metric G tilde. It's a null hypersurface at the boundary. It has other things. It has it's foliated by Lorentz tori. The metric is degenerate, but you can still have tori Lorentz surfaces in this hypersurface. And probably most kind of pictorially, this foliation has two singularities, which are two curves, which are the hop flank in the three ball. So the singularity of these foliations, singularity, is a hop flank. And in fact, this hop flank, what are they? Essentially, every null, every geodesic, space-like geodesic, so one with positive norm, starts on one of these and ends at the other side at infinity. So this is like the space-like infinity, and this is the time-like infinity. So all the time-like geodesics start and end. Infinity. So in this conformal compactification, somehow the causal structure can be seen in this link in the boundary. Okay, so this is a general philosophy of the work that we're doing at the moment with myself and Wilhelm, is that if you have a four manifold with boundary and you put a neutral metric on it, you can see remnants of the interior of the four manifold in geometric data at the boundary, such as this. Okay, under optimal conditions, etc., of course, which I'm not going to go into in great detail at this point, but that just gives you an idea. And this is the simplest case. This is when you're just talking about R22. Right, so this is ground zero state. Okay. So once again, here, somewhat more importantly, what we're seeing with the neutral metric is some geometric data at the boundary, which is telling us something about the four-manifold interior. Okay, so this is just my general idea about geometrization and how some support for this proposal. Okay, so now we ask the question, well, what kind of questions you want to answer in four manifolds? So let me now go to the second part of my talk, which is to describe Casson analysis. I won't go in great detail, but they're not so complicated that you can't understand what it is that Casson did. And as far as I can see, these really are the key thing to understanding the difficulties in four manifolds in terms of exotic structures, etc. This is really the key thing. So these were originally in lecture notes that Casson gave a series of lectures in 73, 74. They were later published in 79, kind of, in a book when they were brought out of, somewhat out of obscurity, although they were well known, I guess, in the topological community. Okay, so let me state clearly exactly what Casson did. So let W be closed, sorry, not closed, smooth, simply connected, I'll assume it's connected, I won't bother saying that, simply connected four-manifold boundary. So again, this is the boundary case with boundary W. Okay, next you look at those, let's say let. We have a series of maps which take the disk and boundary into the four-manifold and its boundary. So the boundary of the disk lies on the boundary of the four-manifold. And what we want these to be smooth immersions. So they're allowed self-intersection, they're not necessarily embedded. Smooth immersions. Moreover, I guess they're embedded at the boundary. You don't want any self-intersection at the boundary. Embedded at the boundary. Such that, okay, there's a few conditions we're going to have to put on them. I mean, they're fairly straightforward, but of course you have to enunciate them. First is that for I not equal to j, that they don't intersect at the boundary either. F of intersection of I is intersection F j of boundary. It's empty, so they don't intersect at the boundary, so the boundaries are separate as the two disks. Secondly, we have a homological condition that Fi dotted with Fj is 0. So there's a homological condition. So you kind of think that you'd like to separate these two. Somehow they're not linked together in such a way that you would that you can't separate them. And in fact, the idea now is to try and somehow push these things apart, and then you can do some topological machinery. Now, leave that there. I'll come over here, slightly out of sequence, but. Okay, that's the second condition. The next condition is homological, and then we'll have the payoff. Okay, so suppose there exists elements in H2 of W such that one Bi with Fj is delta Ij. And the second thing that you need, so this is a homological condition, beta I dotted with beta j is even. Okay. So we don't need to worry too much about it. Just there's some homological condition that tells you you want to try and separate these two disks, these disks, a set of disks, and then we can do some kind of topology on them, and they have the prerequisite homological conditions for you to be able to do it. And now you ask the question, well, can we separate those disks? Can we separate them so that they don't intersect? Can we make them so that they're embedded rather than immersed? Okay, so Casson, what he did was said, yes, you can up to homotopy. So what he said is, there exists these surfaces in W such that, so these are open, he called them open sets, let me just word them exactly right, disjoint open sets, but so there exists for each disk, there exists a set, so you get these disjoint open sets such that the following holds. The first thing is that this intersects the boundary in, just use right, yeah, Fi of the boundary of D cross R2. So they intersect in a neighborhood of the boundary of each disk. You want to intersect the boundary of your four manifold. In fact, sorry, I should say homotopy equivalent. And then finally that Vi with its boundary is homotopy equivalent to the two disk cross R2, two disk with boundary, S1 cross R2. So what this is saying is they look like just solid a disk with boundary cross R2. They look like it in a homotopy sense. So these are homotopy. So his construction is essentially you have these self-intersections that you want to get rid of, so you attach another disk to get rid of that self-intersection, try and pave over any loop that the self-intersection has caused. But unfortunately your new disk will have a self-intersection, so you do it again and again and again and again. And in a limit, it weakens, but at least you get some kind of homotopy properties that it looks like, these things look like a two-handle. This is what they describe as a two-handle.
So here Fi you consider as element of relative homology.
Yes. So the picture really is as follows. So here's your W in here. Suppose this is your W, there's your boundary, and you have these disks. What do they look like to start with? Well, your disk has kind of got self-intersection. We're having the dimensions, so there. It's got two self-intersections. So what are we finding? We're finding these W's, so that's one of the disks. Well, forget about separating them for the time being. Let's just focus on it. So what you're saying is you kind of have this VI, which contains, so this is your VI, which contains your disk DI or F of DI. And so you have this neighborhood, and while your disk sits inside this, it looks, and this thing here has the kind of the right homotopy properties. You're not sure it really is a regular normal neighborhood of an embedded disk. And that becomes the question. When this was done, so I guess one thing that Casson, he did this in 73, 74, but the issue is, well, homotopy is so weak, Homotopic is kind of a weak property. We would like at least homeomorphism or diffeomorphism, obviously, if we want to talk about smooth four manifolds, as Casson was interested in. But in any event, the argument leads to something that's possibly weaker than you, and there was no obvious way to extend that or to go any further. Okay, but this somehow is crucial, this homotopy here. So let me just note the following. So if this homotopy equivalence can be strengthened to homeomorphism, and this is Friedman in 82 paper. If you can go from homotopy to homeomorphism, you immediately implies four-dimensional topological Poincare conjecture. I shouldn't say the word. I shouldn't say immediately, but at least it leads to it by well-known topological method. It proves the four-dimensional topological. In fact, it gives you a lot more. It gives you the topological classification of four manifolds. Simply connected four manifolds. Okay, so this somehow is key. This is the key thing. And I guess Casson's work in the 70s was given new prominence in the early 80s precisely by this fact that Friedman says he can go from homotopy to homeomorphism, and then as a consequence you end up with this big classification. On the other hand, it cannot be strengthened to smooth in many known cases. So this cannot be smooth. So that this is smoothly equivalent to a two-handle. If it were, it would contradict Donaldson ultimately if you go back, right? So this is the smooth side of the picture is of course Donaldson shortly after Friedman. I should say the word usually, because some of these, it's known for certain ones of this that they can't be smoothly homotopic, they can't be smoothly equivalent. It's not a smooth handle, but On the other hand, by the way, when I say Casson handles, that's what these VIs are, I should say. The VI is the Casson handle, that's what the name of it. And it's constructed by continually, you know, let's say, kind of cancelling each. You see these nice pictures in these topology books where they kind of have the dimension and give you these line pictures of what's going on. But it can't be smooth. So immediately from that, you can then say, in fact, this now gives you the basis of the dichotomy between topological, homeomorphism, and smooth. So ultimately, this all leads to exotic structures, it leads to exotic morphores. So you really have to roll, you can roll the whole of modern four-manifold, the understanding of four-manifold today, back to just stiffening that one result. Okay, but the question still remains. It's still not known how many of these Casson handles are smoothly equivalent to a standard two-handle, or how many of them are exotic in words, I guess, that will be used nowadays. Okay, so we've gone quite far. So now what I'm going to say, I'm going to start backing, and we're going to go back to Joachimsthal and see how I've managed to kind of pursue a program of understanding Casson handles and ended up back with surfaces in R3. So let me address the issue of what we mean by slice. So the question with this is, it has the right homotopy type, but is it homeomorphic or is it diffeomorphic to a regular two-disk cross R2 with this right, stuck into the manifold in the manner in which you want it? So you can ask a simpler question, say, well, do we even have one embedded disk that has the right properties at the boundary that sits inside it? And that's the question whether this VI is sliced. So the question is, does there exist? Now, I'm only going to talk about the smooth case. I'm not interested directly in the homeomorphism case. I'm going to do it in the smooth case. And the intent is ultimately push it down to try and understand this weirdness at the level of homeomorphism. So does there exist a smooth, embedded disk in VI, in one of these Casson handles, which is attached in the right way. It has to have the right framing, etc. There's some technical thing going on. So with the right, let me just say boundary conditions. Now, what you could do is just take your initial disk with its self-intersection and look at its boundary and just say, do I have another disk that sits in there that's embedded, that has the same boundary, whereas homotopy equivalent to the boundary of the original disk. Okay, so the answer, so this is the slice problem more generally. I mean, normally what you do is you take S3, you take a curve, you ask, does there exist an embedded disk in the 4-ball bounded by the 3-ball by S3, whose boundary lies on that curve? So that's generally the slice problem. So this is just the specific case where I'm interested in trying to find out whether these Casson handles are in fact slice, smoothly slice. Okay, so what's the strategy and what has any of this got to do? Notice now a bit of geometry in sight, although I guess some might argue that Friedman's H2 proof is a geometric proof in the sense that it involves shrinking and some geometric topology from the 50s and 60s. Let me just now address then how am I going to attempt to use a neutral metric to answer a question like that. Okay, so the approach is, so first of all, let's take, again, a simple case, a complex four-manifold, so I mean it's a real four-manifold with a complex structure. So take W and J, so it has some complex structure on it, and suppose you take a surface, closed surface, sitting inside it. Well, then we have, well actually this doesn't have to be embedded, let me allow it to be immersed, because this is the issue that we're trying to go from immersions to embeddings, that's somehow the issue. So a closed immersed surface, then I is the Euler characteristic of the surface plus the homological self-intersection minus 2 minus 12. Okay, so what is this? Here, this is the number of complex points on S. Now what is a complex point? So a complex point, you have a complex structure J, and it's going to take, if you have a surface in there, you can apply J to the tangent space, and in general you'll get some other one that's no longer tangent. So the question is, if J acts on the tangent space at this point, if it leaves it the same, if it gives you back the same tangent space, well then it's a complex point. So if you write it as a function, as a real function of a graph, it's going to be holomorphic at that point. So it's a pointwise notion of holomorphicity. So in general, if you take a closed surface and you wiggle it a little bit, the complex points will be isolated. And each of them will have an index, and the total number counted of index is the topological invariant of the surface. As you can see on the right-hand side, these are topological invariants, and it's the number of complex points on the surface. Here, your Euler characteristic, I won't bother saying, this is your homological self-intersection, and D is the number of double points counted with. I make them generic, so they're plus or minus, and then add them all up. Okay, so this is the strategy. The strategy is to use a relative version. This is for closed case. This is the closed case. So, how are we going to check if something is slice or not, or at least attempt some method or ideas as to how we can get at it? The idea is as follows. Take a neutral Kaehler four manifold. So it has both the neutral metric and the complex structure. And from this formula, try to control the complex points, the homological self-intersection, the genus we're usually working with, in order to find an obstruction for the number that D is not zero. Okay, so let me put it a bit better than I just said it. So taking and with boundary, of course, use a relative version of the boundary of lie to control, and control, in which, let me just say, in circumstances where we can control, we have control of these quantities. To show that your D can't be zero. Right? So it's an obstruction to slices. So in other words, we give you a circumstance with a relative version of this, where I can tell you the number of complex points on any disk that's attached to a particular curve. I have some control of the homological self-intersection, and I can tell you, oh, there must be double points in the interior. Right? So that's the idea, is to show that D can't be zero in certain well-defined situations. Okay, so finally.
Sorry, what does lie mean?
So there, this is the lie formula I should have taught. So this is the lie formula from 1972. So that's the lie formula. So that's for closed. It stays closed there, but a relative version with boundary conditions. So you have, okay, there's some subtlety involved in all of this, but the basic idea is, can we control these for disks attached to a given boundary? Right, that's the idea. And if we can, well then perhaps we can find circumstances which we can tell that there must be double points in there. So we can say there's no embedded disk with that boundary. Okay. Now, that is more or less what this Joachimsthal global version gives you in a very special case. So this is finally come back to the final part of the talk. So the first part, first and final now, is what has this all got to do with surfaces in our tree? Okay, so my final thing. So global version of Joachimsthal. Okay, so there's no four manifolds around or anything. I'll now show you where all that comes in. So let's start off. So the basic idea is, if you take the space of oriented lines in R3, then it is the tangent space to the two spheres. It's a four manifold. It's a non-compact four manifold. It's a tangent space to the two spheres. Of course, this is the space of oriented lines of Rn is Ts, right? 2n minus whatever. Yeah, so you can do this in any dimension. However, as I've said, you have to use somehow in a topological classification or in a geometric classification of sort, you have to use some specialness in the dimension. And the fact is, in this dimension, the space of oriented lines admits a neutral Kaehler structure. So a neutral metric, a symplectic structure, and a complex structure all fitting together in the standard Kaehler manner. But again, this metric here has signature plus, plus, minus, minus.
Is that a parity structure?
Not Kaehler, no. It's just an honest-to-God symplectic structure, an honest-to-God complex structure. Standard complex structure that you lift from TS2, in fact. So it's just a complex, it's not the para-complex structure as you would have for para-Kaehler. But when you put it together when you put these two things together, you have a non-degenerate symmetric matrix, but it's eigenvalues are not plus, 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 right? It's plus, plus, minus, minus. So it's slightly unusual and very little literature really on such metrics, and this is one of the reasons I'm kind of highlighting that as a kind of a key new ingredient in all of this. Okay, so it admits such a thing. Okay, so what? Such that the isometry group of this metric G is the same as the flat Euclidean in R3, the Euclidean motions in R3. So what that allows you to do is that you can kind of model all these things that go on in R3 with the Euclidean metric by structures and submanifolds in this four manifold with a neutral Kaehler metric. And in the Theorem we played this game a certain way, and we took a problem in R3 and we solved it in the four manifold. Now what I'm trying to do is do the exact opposite. I'm trying to take four manifolds, which can be terribly complicated, and say, well, your neutral metric allows you to get a nice picture of what's going on in R3 or in any constant curvature 3 manifold, and you can then kind of construct interesting new geometric models. Okay, so this again, so this is in this dimension, so this is not true for any other dimension. So this only works in dimension 3. The space of oriented lines in Rn admits a metric which is invariant under the action of the Euclidean motion if and only if the dimension is 3. Okay, so this is one of the kind of unusual aspects of this thing. It's an accident of low dimensional Lie groups, really. Okay, so now we finally come back to surfaces. Okay, so this is our background picture of the whole thing. So you have your surface in R3. So what I'm interested in, so if S is a smooth convex surface, I'm going to introduce two things. The first thing is, well, let me call it NOR of S, which is the set of all lines. So again, I'll use this identification TS2 as the space of oriented lines, so I'll call it gamma. So it's a set of all, so the normals of S are the normal lines. Right? So gamma of S such that gamma is perpendicular to S where it intersects it, and outward pointing, using oriented here. Outward pointing. So this is the set of all normals to your convex surface. This is obviously, I'll call it sigma maybe. This is, it's in TS2 and it's a surface. Okay, so if you take a surface in R3 and you look at the set of oriented normal lines, well of course this is not a norm, this is not a generic surface in TS2, it has some properties. So sigma is Lagrangian with respect to the symplectic structure, and actually it's a section of TS2 because it's convex. And it's a section of the canonical bundle. You can parameterize it by the direction of its normal. So these are this is a very special kind of surface that you've chosen in TS2. That's one thing. Okay, so we exploited this heavily in the proof of the Kaehler-Theodori. What I want to talk about now is in fact the tangent lines to S. So what are the tangent lines to S? And what I mean by that is the set of all oriented lines which are tangent to the surface. So it's an element of the tangent space that you can allow me that kind of orientation. So we look at the set of all oriented lines that are tangent to your surface. this is a hypersurface. It's a 3-manifold in your 4-manifold. In fact, we'll talk about it in a second. It has, again, this is a very special set hypersurface. What is it? Well, it has the following properties. One, it's a null hypersurface with respect to this neutral metric. What's more, convexity of the original surface in R3 implies that it's a pseudo-convex surface, or a pseudo-convex hypersurface. What do I mean by pseudo-convex? Well, that's standard meaning. You have a complex structure, and on this 3-manifold sitting in the 4-manifold, you have, at each point you'll have one complex plane, and if this complex plane is contact, well then it's pseudo-convex, and that's the case here. So in fact, it's if or only if pseudo-convexity for this hypersurface in the 4-manifold is exactly convexity of the surface in the 3-manifold. Right, so again, we're trying to exploit as much as possible this accident of low dimensions, which allows you to transfer geometric information from a surface in a 3-manifold to submanifolds of different dimension, in fact, in a 4-manifold. Okay, so as you can see, what we have there is a very restricted set of circumstances, or at least a lot of geometric information about these hypersurfaces. So now, let me finally make the link. So let W be the set of all oriented lines which intersect this surface. So you take your surface in R3, and you take all the lines that intersect that surface at any point. So this is, it's obviously a subset of TS2. It's a 4-manifold with boundary, 4-dimensional submanifold with boundary. 4-dimensional submanifold with boundary. And what is the boundary? Well, what is the boundary of that? It's the tangent space. It's the hypersurface, right? So the boundary is exactly this hypersurface. I might call it H or something. It's H. Now, we don't have one surface, we have two. We have S1, and then we have another surface intersecting. Well, just look at the disk that intersects it. Just take the D2, I call it. Okay. So this is D2, that's S1. Now, here I'm doing the orthogonal case of Joachimsthal. I could change the definition of tangent and I could do the constant angle of any angle. Here are orthogonal. Because what I'm interested in is this disk here and its normals. Well, if it's an orthogonal intersection, the normals will intersect the tangent. So what we've done is we have these two sets. We have the normals to this in this 4-manifold. We have the tangents to this, which is a boundary, and then they intersect. So the picture we have is some hypersurface, again, I'm going back to the 2-dimensional, and you have a disk attached to it. So this is your H, and this is the normals to D. So maybe I'll call it the tangents of S1. But this is slice, okay? I'm not claiming this is embedded. It's an embedded disk. There's no issue with sliceness or not here. But what it is telling us is from this S1, we can control the number of complex points inside here because it's given by the data in the boundary. Okay? So the question I had asked about you, or the approach I had suggested with regard to controlling quantities in Lie's formula, this is the first thing. I guess I should have said it a second ago. The reason is umbilic points in R3 of a surface in R3 correspond exactly to complex points of the normal to the surface in TS2. So this is, of course, what we used a lot in the proof of Kaehler is this relationship between umbilic points and complex points. They correspond exactly. So what we've done is, if you think of your S1 and the tangents as a boundary, we've attached a disk to it, and we're controlling the number of complex points based on the number of complex points the boundary curve has in the surface S1. Okay? So what we've managed to do, as a special example, so the upshot, we can control the number of complex points on the disk with boundary, what was it, normal D1, by boundary data, namely the curve where they intersect of the tangents to S1, which is the whole hypersurface that you've got control of. Okay, so that's just one quantity that I've managed to actually say something sensible about. And this is not the slide, these are slice, okay? So this is slice, obviously doesn't have self-intersection. So again, this is the simplest possible case in which we can see that our neutral metric. Okay, so how do you prove this? Well, in fact, you prove this by just a computation. Now it's just really a computation, but again, it's the philosophy behind it that I want to try and emphasize. So the proof follows just by direct computation. And why does it follow from computation? Well, these are rather special things. This is a pseudo-convex surface. This is a Lagrangian, this is a pseudo-convex hypersurface. This is a Lagrangian surface. It intersects in a curve that's transverse to the contact structure. Right? There's a whole heap of information, geometric information that you have on this whole scenario, which allows you then to compute the winding number around the boundary, and it relates it to the winding number in your original surface S1. Okay, so let me just then finish with the sketch as to how we're going to try how this insight, if you like, or this particular perspective on the problem would play out with regard to Casson handles. The first thing is, what you would do is take your Casson handle and embed the Casson handle properties of the boundary. The Casson handle goes to the boundary of your four manifold. So embed your Casson handle in a neutral four manifold. In particular, we'll take TS2 as the simplest model. Neutral four manifold. Neutral Kaehler, in fact, is even better. Secondly, compute these invariants. All of these invariants, the number of complex points, the Euler number, the homological self-intersection, we can use geometric data to control the topological invariance of disks with boundary, right? The slice disks that we're trying to find. You try and find a disk and say, well, it might have a self-intersection, but then you use Lie's formula to show that it must have self-intersection. So you'd have an obstruction then to sliceness. So dot, dot, dot. The ultimate thing would be to prove no Casson handle is smoothly sliced. So they really are odd things. And that's, probably most four manifold topologists would believe that that's true, that Casson handles are never smoothly sliced. As I say, there's certain cases where this is known, but basically no one has come up with a suggestion as to how we might actually try and do it other than a piece-by-piece case. So here I'm just giving a sketch as to how this might go on. Of course, many technical complications involved. I've taken just the simplest case just to illustrate the basic idea. So I think my time's up, so thank you very much for your time.
Oh, thank you very much, Brendan. Yeah, very interesting, very attractive. It's great. Any questions?
This sketch in the end, I mean, it doesn't refer to this generalization of Joachimsthal. It's just.
Oh, sorry. Okay, so I guess I should have said that. So the picture that I have here is of this disk, this Lagrangian disk attached to a pseudo-convex surface. This very specific that you can write down with your bare hands, and your curve is a transverse curve with respect to the contact structure. So then what you do is you write down the relationships of the intersection and differentiate them, and you find that there's a relationship between the winding number which detects complex points in here with the number of complex points in the complement in this. So it's a computation. So I guess Joachimsthal's theorem, you'd say, is just a computation now. In some sense, our theorem is just, it's a computation, but the global aspect of it is, I guess, the new aspect, but this particular perspective is what I've emphasized rather than the computation per se.
So,
yeah.
How is it that the neutral plus plus minus minus rather than any other neutral signature means that you're going to expect the same, that you expect the same situation possible for a Casson hand?
Okay, so I guess the point, there's a couple of different ways to answer that. One would be that, in general, plus plus minus metric is good for codimension 2 problems. Because of the signature, it's good for codimension 2. So you can look for positive disks and you can deform them, etc. So codimension 2 problems seem particularly well suited to a neutral approach. That would be the first thing I would say. So Casson handles are all to do with disks, adding disks, etc. So you have to control pi1 all right along the way, and there are various technicalities to do it, but essentially it's an issue again of codimension 2. So from the point of view of neutral metrics, see and adapt themselves to codimension 2 situations better, and that would general philosophy that we would apply this to Casson handles. The other thing I would suppose, so the big difference between a neutral metric and a definite metric in the Kaehler case is that if you take a Lagrangian surface in the definite case, it can't have any complex points. Right? So Lagrangian sits over here, complex sits over here, and usually that's the way you play the game. For a neutral metric, that's not the case. You see, you can have Lagrangian surfaces with complex points. Okay, so what that means is, if I were to take a disk here, with some kind of, I would like the boundary to be totally real, so the boundary does not have any complex points in it. And I ask you to deform it to a Lagrangian one without introducing complex points. You cannot do that in the definite case, but you can do it in the indefinite case. You see? Right? Because you have to push the complex points over the boundary in order to make it Lagrangian in the definite case, but you don't in the indefinite case.
Okay, so that's actually surprising, because Lie's formula really, I sort of interpret part of it as information about normal numbers, but this is not the case anymore in neutral metrics.
Well, so first of all, the last one I wrote up there was for closed, and of course you can take your homological self-intersection, and this of course is, the normal one.
Yeah.
Yes. But when you have a disk, don't forget, a disk with some boundary condition, it's going to be more subtle. It's a relative first Chern class. So there's a gap there as to, I just said use a relative version. I just used 2 words to hide a lot of that complexity. But certainly you have to have this boundary condition, which you insist remain totally real. And the point is, you see, you can't do that in the definite case. Well, you can't get to a Lagrangian interior if you're going to do that in the definite case, whereas in the indefinite case, you can do it. But the failure, is the complex points. And so you just can't.
Any further questions, comments? If not, then I think it remains to thank Brendan again for a really interesting talk. Thank you.